Петрович Piatnitski. Можно попросить? Да. Мы можем переговорить. Давайте.
I would like to thank the organizers of this meeting for the invitation and for the opportunity to give a talk. It's my great pleasure to participate in the conference at this university. And the results I'm going to present and to discuss today were obtained in collaboration with Sergei Pirogov and Elena Zhizhina. Elena Zhizhina is here in the audience, and both of them are from Moscow, from ITP. And my talk will focus on the topic, on results which formally can be understood as probabilistic results. Large deviation technique, it's one of the well-known problem and method in probability theory. But it happens that in this problem, the methods I'm going to use and the approach and some technical details are based on some spectrum properties of a family of non-local operators. So the proof relies on results on analysis and spectral theory and some spectral property of non-local operators. And also this method has many things in common with quasi-classical methods, you will see. So I think, although formally the topic sounds like a probabilistic topic, in fact, there will be many technical statements of quasi-classical and type statements for non-local operators. So the operator we're going to study is the operator, non-local operator, so-called non-local operator of convolution-type. You see, it's operator which has a convolution kernel, which is a of x minus y, and also the function lambda, where a of z is the function which is responsible for the localization property of the operator. The smaller the support of a, the more local properties show the operator. And function lambda represents the so-called local characteristics of the media. If lambda is a constant, then the media is homogeneous. If lambda is not a constant, then a particular property of the media depends on the particular point where our particle is. And since the operator is non-local, this function, which represents the characteristic characteristics of the media, depends on 2 points, x and y. So one can, in fact, easily check. It's a simple computation to check that if a is an integrable function and if lambda is a bounded function, then this operator is a bounded operator in L2. It's, for example, it follows from so-called Schur theorem. And we are going to study the asymptotic property of the solution of the corresponding boundary value problem or problem in the whole space. It doesn't matter. As usual in homogenization theory, homogenized operator depends on the family of the original operator and doesn't depend on the particular choice of boundary conditions or domain. And we do the so-called diffusive scaling. We scale the time variable with, if we consider the corresponding parabolic problem, which we always have in mind, when we study diffusion problems, we scale time with the square of small parameter and the special variable with the first order, with the small parameter to power 1. And as a result, we arrive at this operator. You see, now we have, oops. Sorry. We are taking a family of operators with a small parameter epsilon, and we call it A tilde epsilon because I will use two different normalizations. This is normalization, natural normalization, which appears in the case of the diffusive scaling, and in the case of diffusive scaling, we have epsilon to power minus d minus 2 in front of the operator. The d plus 2 is formed from two parts. Epsilon to power d, when we change variable, is just Jacobian. And additional epsilon square is coming from the sign scaling epsilon square, which is there. Well, if we want to study the media which is locally periodic, so there is a periodic structure of the media, but this periodic characteristics are slowly changed from one point to another, then we consider the coefficient lambda of more generic form, lambda of x. Lambda is a function of so-called slow variable x and y, which represent the global point in the media, and first two variables represent the local periodic structure. So, in fact, it's known in probability theory, some probabilistic arguments for those of you who might be interested in this probabilistic interpretation of this. We have a process, Markov process, whose generator is either this one or this one. The difference only in normalization. We have d plus 2 here and d plus 1 here. So here the process moves in fact faster. Well, and here the process moves faster, here it moves slower. And what we know that there is a Markov process, which is a process with independent increments if lambda is a constant, and it is just a Markov process if lambda is not a constant. And we are interested in the asymptotic behavior of this Markov process as epsilon goes to 0. We have a family of Markov process of trajectories, random trajectories in the path space, in the Skorokhod space. In fact, this process behaves in the following way. It stays at place for a Poissonian time. Then it makes a jump, and jump is ruled by this kernel. And then it stays another Poissonian time. Then we make change of variable. The jumps are getting smaller and smaller, and the number of jumps is getting larger and larger. And at the end, we have trajectory which at the end, in fact, with probability 1 is continuous. Almost all trajectories of the limit process are continuous. Well, that's the probabilistic interpretation, and we will be interested in the limit behavior of this trajectories as epsilon goes to 0. So we make the following assumption on the function a and lambda. A is a non-negative function, which is L1, and additional technical assumption that it's L infinity. Presumably this assumption can be discarded, but so far we assume this. And then we assume in addition that integral of A is equal to 1. It's just normalization condition. And what is important that we have super exponential moment. You see there is a P which is greater than 1, such that the moment with exponent to power t is finite. Well, and then we assume
it is almost localized.
yes, as epsilon goes to 0, it's getting more and more localized.
Yes, but fast details of A.
I mean, yeah, exponential moment means that tails are very wide, but still around 0 we don't assume anything. We can consider even a function with finite form. Still, localization property, localization will be for the epsilon in this case, but not beta. Yeah, you're right. If you have good exponential moment, then of course localization properties are very strong. Well, non-degeneracy, it's just technical assumption. In fact, it can be discarded at the price of additional technicalities, so I prefer to impose it. This condition is not important. And what is important is the so-called uniform electricity. We assume that this coefficient, which represents the local characteristics of the media, is separated from infinity and from 0 by positive constants. Well, and finally, we assume that our function lambda is periodic with respect to the first two variables. So media is locally periodic. Well, we start with not with large deviation, but with homogenization result for this operator. So what we do, we consider the corresponding parabolic problem. You see, normalization which we use here is still d plus 2. And we assume that media is pure periodic for a while. In fact, the same result can be formulated for locally periodic media, but I prefer, for simplicity of presentation, I prefer to discuss pure periodic media. And we have the Cauchy problem for family of Cauchy problem parameterized with parameter epsilon. Non-local Cauchy problems. So the question is, what happens to a solution since it's a family of bounded operator? Of course, for each epsilon there is a unique solution. For bounded operator, the parabolic theory is trivial. We know, everybody in this audience knows that there is a unique solution for any finite time, in fact, for all times. And now the question is, what happens to these solutions as epsilon goes to 0? Does it converge to something? And if it converges, can we characterize the limit of this? Well, and the answer to this question is obtained was obtained in our joint work with Yelena Zhizhina, and the statement is as follows: there is a constant vector B bar, and there is a constant matrix A bar, such that the difference between the original solution and the solution of this limit problem, but in the moving coordinates and moving frame, the difference conversion is true to 0. So it's not, somehow it's not a convergence result, it's a convergence result in a moving frame. So the limit dynamics, in fact, is decoupled in two different dynamics. One is just the movement with a constant speed in the direction B bar, and with the speed is the order 1 over epsilon. And on the background of this linear movement, there is a parabolic dynamics given by this equation. Pay attention to the fact that the limit operator is local. And of course, we can expect this because, as was already remarked, the support of our kernel is getting more and more concentrated, more and more close to the kernel is getting more and more close to the delta function. So in the limit, we expect something local. But this is the exact formulation. In the limit, we have operator, which is just standard heap equation. It's a constant matrix, positive definite, and there is a convergence, but convergence is a moving coordinates. Of course, if the operator is symmetric, then B bar is 0. For symmetric operator, convergence, we have convergence without any movement. But for non-symmetric operator, we have convergence only in moving coordinates. Well, what does it mean that there is a movement, there is a homogenization in moving coordinates? It means that if we multiply our process by epsilon, that's why we need another normalization when process goes slower. Then, after multiplication of our process by epsilon, the speed is getting just B bar. You remember, in the theory, the speed was 1 over epsilon B bar, but after multiplication of this process by epsilon for the new rescaled process, its limited dynamics is very simple. It starts from the starting point x, and then it moves with the constant speed B bar. That's the limit dynamics of our process. And on top of it, if we use another scale, more detailed scale, we will see that the central limit theorem holds also that around this point there is a diffusive dynamics. But if we want only the rough characteristics, then it just all the trajectories, almost all trajectories, converge that just to linear functions moving with the speed B bar. And now we pose the following question, to which the theory of large deviation gives the answer. What is the probability? So the probability to go near the trajectory x plus B bar t is close to 1. It follows from this result. But what would be the probability to go along other trajectory? If we just draw if we draw some function in the configuration space, what would be the probability to go in the vicinity of this? Yeah, if we start, that's our point x, and if we want to go along some, that's our x B bar, and according to this theorem, almost all trajectories go along this linear function in the vicinity of it. But what would be the probability to go in the vicinity of some other? If we take a delta neighborhood of some other function, what would be the probability to be in this delta neighborhood of some trajectory? It should be small, but how small? Would be exponentially small, polynomially small, and the answer to this question is given by this large deviation theory. And I'm going to so we say that some process in the Skorokhod space satisfies large deviation principle if the following two properties hold. For any open set, the probability that our trajectory belong to this open set, of course it will be open space set in the space of trajectory. Is great or equal than if the infimum over the set of some function defined on the space of trajectories, which is so-called rate function. And for a closed set, we have the opposite inequality. For nice functional in typical situation, in fact, we have just equation. That's inequalities appears when there are some jumps or some irregular, when a rate function shows irregular properties, otherwise it's equality. Well, and the result I'm going to prove today, to explain this today, is the result of large deviation for our process. So our process with generator, which was written, satisfies large deviation principle in the Korokot space with the following rate function. There is a Lagrangian L, which is here. We should integrate this Lagrangian along the trajectory gamma. And this Lagrangian, if the function is absolutely continuous, then this quantity is finite, otherwise it's just plus infinity. The rate function is defined for any element of the, on any trajectory from the Korokot space. But if our function is not absolutely continuous, then it is just plus infinity. So the probability to go along the non-absolutely continuous case is admits the estimate which is super exponential. So it's smaller than any exponent. So what do we know about this Lagrangian? In fact, our main focus now will be on this Lagrangian, how to construct it. Roughly speaking, Lagrangian, okay, it's a continuous function. It's in the first variable, uniformly with respect to the second variable. In first variable, it shows superlinear growth. It grows faster than linear function. This function is convex, and it's strictly convex in the vicinity of infinity. So this function is convex, but we do not claim immediately that it's strictly convex everywhere. But in the vicinity of infinity, this function is strictly convex. And we start with the case pure periodic media. The locally periodic media, its treatment reduced just to some freezing and localization argument. It's very technical thing. I'm not going to dwell on it. Well, first of all, let's see what is known on this topic. In fact, if the media is uniform, if there is no function lambda, only convolution kernel, then this problem was studied in the one-dimensional case by Magulski, and then in multi-dimensional case by Deviation. And the Lagrangian is first Hamiltonian, then Lagrangian. They are constructed explicitly. You see what we should do? We should take the exponent which is written, substitute 1, and this gives us the Hamiltonian. Lambda and t are just normalization factors. So we have explicit formula from Hamiltonian, and from this we can calculate that it's strictly convex, and it goes to infinity exponentially as theta goes to infinity. And the corresponding Lagrangian, then, okay, we make a Legendre transform. We can deduce that Lagrangian is also a strictly convex function, which also grows superlinearly at infinity. So in this case, it's very nice function with the explicit representation. But picture is not so nice in our periodic media. So in the periodic case, there is a first we want to study the large deviation for just one jump for a linear function, and it can be done using the so-called Gardner theorem, and everything is reduced to the family of the operator, which is written here, and in fact, it's like in real quasi-classical analysis, we make a commutation with two exponents. We apply operator to the product of unknown function and the exponent, and then the result is multiplied by exponent of minus theta x. We obtain this family of operators. And what we're interested in is the eigenvalue or the point of the spectrum of this operator. That's a family of bounded operators. These operators are on the torus. We study it in the space of periodic functions. And we are interested in the behavior of the spectrum of this family. We want to know what is the behavior of the point which has the largest real part for this operator. It's not entirely considered in order to study this asymptotic derivative behavior of this operator applied to one. It's sufficient to find the point of the spectrum of this family. Well, this I will skip. So the family, you remember there was a family of operators on the torus obtained by commutation with exponents. And we take the point of the spectrum of this operator, and then we take the point of the spectrum with the maximum real part. It's a bounded set, closed bounded set, so maximum is attained, and we have the parameter which is so-called AS of A theta. Well, and then we can show that in fact our logarithmic asymptotic of our family, which is required in Gardner theorem, you can just forget about it. What we're interested in is the behavior of this spectrum, the spectrum as a function of theta. So that's our family of operators. And pay attention to the fact that since our operator consists of two parts, the second part is multiplication by a continuous function. And this gives us the case of essential spectrum, which doesn't depend on the parameter. When we make the commutation with exponent and multiplication by function, but a function remains unchanged. So this part is fixed, and in addition we have a compact operator. So we have a family of compact operator and a operator of multiplication by a continuous function. And we would like to know what is the spectrum of this sum as a function of theta. So there are two options. It might happen that the presence of this compact operator results in the existence of eigenvalues which are above the upper part of continuous spectrum, or there are no such eigenvalues. So there are two options. Either we have a discrete eigenvalue whose real part is bigger than minus meaning g of x, or there are no such eigenvalues, and then this S of theta coincides just with the minimum g of x. At the beginning, we thought that there is always, when we face this problem for the first time, we thought that there is always eigenvalue in this with real part bigger than minus minimum G of x. By the way, using a version of Crane-Rootman theorem, we can prove that in this case, this eigenvalue with the larger real part is in fact real, and the corresponding eigenfunction is positive. But then we succeeded to construct an example in which for certain area of theta, it is not the case that this family of operator, its maximum of its real part of the space, might coincide with this parameter. So both options are possible. And it was surprising for us. So that's two possible behavior of our function. What we can prove is, I'm not going to write it as a formal theorem, but I'm going to explain you the proof. As long as there is an eigenvalue above minus minimum G of x, the corresponding function f of theta, which coincides with Hamiltonian, is strictly convex. Second order derivative is strictly positive. And this in fact relies on homogenization result, which I explained for a family of operators. As soon as we reach the order of continuous spectrum, after that, of course, it's a constant. And we have this flat part. So this function is convex, but not strictly convex. And then what we can show that the angle at which in multi-dimensional case, the picture is the following. We have some convex domain as a function is flat, and then it's strictly convex as soon as we go away from this set. And the angle at which our strictly convex part meets the flat part, the angle can be positive or zero. Both cases are possible. Well, and that's another option. It might also happen that our curve which corresponds to eigenvalues never touch the border of continuous spectrum, and then it's strictly convex everywhere. By the way, in the symmetric case, we always test this picture. In fact, in the symmetric case, zero is a minimum. So function behaves like this. So what can we say about the property of the Lagrangian? Lagrangian, as I told you, its minimum is equal to zero. There is a unique point where it touches zero, and at this point it's strictly convex. And the typical, it shows Q-Polonia grows at infinity, and it's strictly convex in the vicinity of infinity. And typical picture is like this. It's convex, then there is a strictly convex, then there is a flat part, then there is a corner at zero. There is a jump of derivative at zero. And then at a certain moment it's getting again strictly convex. That's the typical picture. So this way we studied the family of operators, spectral property of the family of operators which were written there. And it's kind of quasi-classical approach because we consider the commutation with two exponents. And then the behavior of this family, it depends on this exponential parameter, gives us the desired large deviation asymptotics. Well, then there is after that some probabilistic consequences. I'm not going to formulate the Gardner-Ellis theorem here. This I already explained, that this function is and as I told you, the rate function is bounded, is finite only for absolutely continuous function. So the probability to be in the vicinity of the function with jump is much smaller smaller than any exponential function. So it's extremely small, even in its exponential. If we take the logarithm and multiply by epsilon, still it will goes to minus infinity. Of course, for locally periodic case, what we should do, we should freeze the slow variable, do all this business, and then unfreeze this variable. That's the standard thing. So, roughly speaking, what we proved that we constructed explicitly this function in terms of the spectrum of our family. The behavior of the corresponding Lagrangian and Hamiltonian qualitative behavior was explained in details, and so in order to give that's our starting point x, and we want to understand what would be the probability to go along some in some delta vicinity of some trajectory. If we want to be. And then what should we do? This probability in logarithmic sense asymptotically is given by the rate function evaluated on this curve. Well, then, unfortunately, I don't have time. There is an example, explicit example, which shows that there are two cases. We can reach the border of continuous spectrum, or we can stay above it. Two different examples. In fact, the second is simple. The first one is non-trivial, but unfortunately, I don't have time, so I have to stop here. Thank you for your attention.
Questions? Was it Alexander? Насколько я понял, обычный мер людей, правильно? Да. А рассматривался в случае, когда это проболевская мера и возможно, что часть меры людей сбивает команду. Возможно ли какие-то?
То есть это комбинация каких-то движения?
Ну, если говорить вероятно, то будет такое течение.
Чисто прыжки, вот если бы удание пришло, то это, конечно, хорошо.
Может быть, непрерывная составляющая внутри, когда такой случай.
Результаты об усреднении были такие, когда там комбинация нескольких, на самом деле там диффузия, плюс
там свойства спектра, такие исследования.
Свойства нет, вот большие уклонения я не видал.
Да. Тут вопрос, наверное, вот нельзя ли оператор шлёпки переписать оператор? Тогда, значит, если так не можно сделать, и так и науку массу. Да, да. Сразу много чего показать, что последний, как это делать, но
да, ну известно, что в больших уклонениях альтернативный подход. Это it's well known that in large deviation technique there are two approaches. The approach in terms of Gartner's theorem, localization and so on, direct probabilistic method, and another approach is through viscosity solution technique and as you suggested. And in fact, now we try to apply this technique which relies on pure viscosity solution, pure viscosity solution analysis. So we hope it will also work.
Then they use actually they use some classical analysis for the phase, but they instead of the name of the phase is the classical. This is just action function, but they call it pseudo-potential. Because they didn't know about the connected.
Here we can also introduce the notion of pseudo-potential.
Pseudo-potential is like just action function. Because if you express it via the Lagrange,
Предлагаю благодарить. Значит, кофе-брейк находится в столовой.